Transformation of functions. The following example is an example of vertical shifting. So here, if you add a constant to a function, it shifts that graph vertically. So notice here we have our parent function f of x equals x squared. But if we add a constant, a c plus c, notice if we go up 3 units from our original quadratic function. We go up 1, 2, 3 and end up in 3 units up, but the same shape. Likewise, if we go 2 units down, minus c here, we go down 2 units. Same shape, but 2 units down. That's an example of vertical shifting. Vertical shifting, we're going up or we're going down. And the way you can tell that it is vertical shifting is because you have your original parent function plus some number or minus some number. You have the parent function plus some number or minus some number. But next we have an example of horizontal shifting. Horizontal shifting. Let's talk about horizontal shifting. So you have a case where you see that we still have quadratic functions here, but you can tell that this is horizontal shifting because our squared is, see how that's on the outside of something that's enclosed. So that square indicates that it's quadratic. If it was a 3 out on the very outside of something enclosed, then it would be cubic. That would be an entirely different shape. But notice it's enclosed in something. When I mean enclosed, I mean it could have been the absolute value. It could x plus 4 could have been enclosed in the absolute value symbols, or it could have been enclosed under our square root. That would be the square root function. So different shapes, but notice that it's enclosed in something. That is horizontal shifting. Now, horizontal shifting does the opposite of what you think it's supposed to do. Notice that our original quadratic is where it normally is at the origin, symmetric to the y-axis. But notice that g of x equals x plus 4. You thinking you're supposed to go right because it's plus 4. Nope, you go left. And that definitely works because at -4, you have -4. If you plug -4 in, notice you will get 0 squared. And that is the point, -4, 0. So when we plug in a -4, we do get 0 as our y. So we definitely have a point right here on that graph. And if you plug in more numbers, if you plugged in, I would say let's plug in -3, for example. You get positive 1 squared, 1. So that point would be -3, 1. Notice it's -3, 1. So yes, it's definitely going left when you have plus 4. But if you have minus something for horizontal shifting, you actually go right that many units. So notice in purple, it went right 2 units. So x plus 4 squared went left 4 units. X minus 2 squared went right 2 units. So again, horizontal shifting is enclosed inside of the function. We have stuff enclosed inside of the function. If you have plus c for horizontal shifting, goes left. If you have minus c, it goes right. Now let's look at an example. F of x equals square root of x minus 3 plus 4. So as you can see, we already have the square root function, right? That is f of x equals the square root of x. That is our parent function. That is where this function originates from, the square root function. Notice that one, that square root function is in pink here. Well, not pink, black here. Down here, this is where it normally lives, just the square root of x. Just the square root of x is right here. But notice this part is enclosed inside of something, right? So that part is horizontal shifting. So this part right here is horizontal shifting. It's enclosed under something, inside the parent function square root of x. So that x minus 3 part, because it's horizontal shifting, it will go opposite of what you think. So you think it goes one way, but it actually goes to the right 3 units. So that's why just that piece of it, just the square root of x minus 3, will go over 3 units. Same shape, it would just go over. Now, what about all of it at the same time? So that plus 4 part on the very outside will give us our vertical shifted. All right, so that's why from this function here, the square root of x minus 3, you can go up 4 units and land here where we have the pink graph. So this graph embodies all of this. F of x equals the square root of x minus 3 plus 4. So the shifts are the following. There was a horizontal shift. There was a horizontal shift. Where? To the right. 3 units. But there was also a vertical shift up 4 units. Up 4 units. All right, let's move on to this section. Write an equation for the new function described. So we're going to go backwards, and based on a description, then we write out the function. So it says the shape of the quadratic function, but shifted 3 units to the right and 7 units down. So what I want you to do is figure out how can you write it like in this form. All of it. First of all, if it's asking us to write a function, right, I always want you to start with the notation for function. You can always use f of x for that. F of x, if it's a function. Now let's break this down. The shape of the quadratic function. We know the parent function is, for that part, x squared, right? F of x equals x squared. But shifted 3 units to the right. 3 units to the right. So if it's going left or right, that's horizontal shifting, right? So we know it's going to be enclosed inside of something, and it's going to go opposite of what we think is going, right? So if it's shifted 3 units to the right, I'm thinking plus, right? But it's not. It's x minus 3, and notice that square goes on the outside. It does not go on the inside. Let's go back to it. Squared is not on the inside, it's on the outside. All right, so if you have some power, it goes on the outside of the parentheses, not on the inside. I see that mistake all the time. Not on the inside, but the outside. And then we have 7 units down. Now that's vertical shifting, and vertical shifting does exactly what we think it's supposed to go. So if it's down, then we know it's minus 7. So we have f of x equals x minus 3 squared minus 7. Now, how would you plot that? Well, normally the original parent function is somewhere here, but we're gonna basically use that middle part as an anchor, and we are going to shift this shape somewhere else. So we're gonna go based on the description. It's saying shift 3 units to the right. 1, 2, 3. Right? We go to the right 3 units and 7 units down. 1, 2, 3, 4, 5, 6, 7. So we land there at the point 3, -7. So that's the middle part of your parabola. I call it my anchor point. So that is f of x equals x minus 3 squared minus 7. And you can always verify this using Desmos.com or GeoGebra. Okay, you can use these websites to graph functions. The shape of the absolute value function. All right, first of all, we know that's the absolute value are these vertical bars like that. So f of x equals, that's vertical bars, but shifted 4 units to the left. Okay, again, that's horizontal shifting. And it's going to be enclosed, and it's going to be opposite what you think it's supposed to do. So shifting 4 units to the left, we're thinking negative, but it's actually plus 4 inside of those vertical lines there. That's your absolute value symbol. And 8 units down. So that piece right here, 8 units down, that is the vertical shifting. And it goes exactly how you think, minus 8 units down, minus 8. So normally our V is here, right, in the center. But we're going to use that middle part like an anchor and shift it. And according to the description, it says shift it 4 units to the left. 1, 2, 3, 4. All right. And then we're going to shift 8 units down. 1, 2, 3, 4, 5, 6, 7, 8. We are here. That is the very center of your V, like your anchor or your vertex or your minimal point, whatever description you like.